Today we're going to talk about Chapter 9, and we're going to get started by talking about sample means. So as we go through Chapter 9, we're going to see a lot of similar problems that we saw to Chapter 7 and Chapter 8. So in Chapter 7 and Chapter 8, we learned two important techniques for statistical inference. The confidence interval, which was in Chapter 7, and the hypothesis test, which we just talked about in Chapter 8. In those chapters, we applied statistical inference for population proportions. So every problem that we did in Chapter 7 and Chapter 8, we were thinking about percentages or population proportions. In this chapter, we're going to use the same two techniques. So we're going to talk about our confidence intervals, we're going to talk about our hypothesis test. Before we do that, we're also going to talk about our central limit theorem. But instead of making inferences about our population proportions, we're going to be talking about the means of our populations. Okay. So just to kind of review, in this table we have some, well not some, but pretty much all of our different notation that we've looked at throughout the semester. So in Chapter 7 and Chapter 8 we were focusing on this last row of this table. We were talking about our sample and our population proportions. In this particular chapter we're going to focus on the top row of this table. We're going to talk about our sample means and our population means. So just kind of a reminder, when we are talking about our population means, we're using mu. Sample means we're using x bar. Standard deviation for our population, we use sigma. Standard deviation for our sample, we use the letter S. So let's look a little bit closer at our sample mean. Right, there's three characteristics: accuracy and precision, which we've talked about in previous chapters. And then we've also talked about our probability distributions, our sampling distribution. Right, so there's not really anything new here. Again, accuracy, we're thinking that the sample mean is unbiased. Precision, the more observations we collect, the larger our sample size, the more precise our mean. And then our sampling distribution are shapes of our distributions, again, similar shapes that we've been seeing all the way back to Chapter 2 when we started talking about these. All right, so a little bit more on our accuracy and precision. If mu represents the mean of our population and sigma represents the standard deviation, our sample mean is unbiased when estimating the mean. And then our standard error is a slightly different formula than the one that we've seen before. Our standard error for our sample mean is going to be sigma divided by the square root of n. So a newer formula that we're going to be using as we're going through this chapter. One key thing to remember, right, as our sample size increases, the sample mean becomes more precise. Right? So what this means is that our sample mean becomes more precise, and then we can also see down this page a little bit, also as our sample size increases, our standard error decreases. Right? So remember, our standard error is related to precision. Our mean remains the same, right? But we're thinking about how far out our curve is spread. Right? If we look at these bottom three images, they show different sample sizes. So in this first one, our sample size is 100. In the second example, our sample size is 400. And then the last one, the sample size is 900. Notice that our curves become taller and skinnier, right? They're less spread out. Our standard error, or standard deviation is getting smaller, and our sample mean is becoming more precise in all of these examples. So we're going to finish off this section just with one example, kind of looking at some different things related to this vocabulary. A student has a large digital music library. The mean length of songs is 258 seconds with a standard deviation of 87 seconds. The student creates a playlist that consists of 30 randomly selected songs. Is the mean value of 258 seconds a parameter or statistic? And then we are asked to explain. Right? So we're going to say that it is a parameter. Right? And it is a parameter because it is the mean of the population. Right? Remember that parameters go with populations and statistics go with samples. Right? So this is a population. Again, when we're thinking population, we think the word all. So this is the mean of all songs, right, in this digital music library. So what we have here, it's a mean of our population. Okay. Right, so then the student is going to create a playlist that consists of 30 randomly selected songs. Right, what should the student expect the average song length to be for his playlist? Right, so the average for the playlist should be 258 seconds. Right? And the reason is the sample mean is typically the same as the population mean. Right. So we should expect that if we take a sample out of our population, that the sample mean that we get is going to be the same as or relatively close to our population parameter. What is the standard error for the mean song length? All right. Our standard error is sigma divided by the square root of n. So we look back up to our problem, our standard deviation, our sigma is 87 seconds. Divided by the square root of n, so divided by the square root of 30, gives us 15.88 seconds. All right. So compared to other standard error formulas that we've seen previously, this one is pretty simple, pretty straightforward. Okay. Would a playlist of 50 songs have a standard error that is greater than or less than our answer to part C? Explain. All right. So if we think about this, our standard error here was based on a sample size of 30. Right? So now we're going to increase our sample size to 50. Right? So if we increase the sample size from 30 to 50, the standard error for the playlist of 50 songs would be smaller. Right? Because standard error decreases as sample size increases. Right, so going through this section, again, just kind of a review of some of our different vocabulary, our relationship between our population means and our sample means. We've introduced a new formula for standard error, and the key thing we want to think about, right, standard error decreases as the sample size increases. As standard error decreases, right, the sample mean becomes more precise.